Okay, so this is the last section, and we're going to look at the derivatives of exponentials and log functions. So we're going to start with the derivative of e to the x, and we're going to do a proof of it and then a couple examples. So when we look at the proof of it, we're going to go back to our traditional definition of a derivative to do the proof. So we're going to take the derivative of e to the x, okay? And we know that our good old definition, I'll put this in red over on the other side here. I just need a red pen here. Not giving me a red pen here. All right, so I'm just going to write in black. So over here, we know we're going to do f of x plus h minus f of x over x, and we're going to look over h, sorry. And we're going to look at the limit as h approaches 0. Okay, so that's our good old definition. So that's going to be the limit of e to the x is going to be the limit as h approaches 0 of e to the x plus h minus e to the x all over h, okay? This minus, I'm going to just move up here just a little bit here. Let's fix that. So I'm going to take this, and this is minus e to the x. Okay, so this is an h right here. All right, so now I'm going to clean this up a little bit. So this is going to be equal to the limit as h approaches 0. Now, when I have e to the x plus h, properties of exponents say that that can be e to the x times e to the h, okay, because that makes x plus h minus e to the x all over h, okay? Again, what I'm doing right now is a proof of what the derivative of e to the x is. Okay, so if I do that, the limit as h approaches 0, what I'm going to do is I'm going to factor out, excuse me, I'm going to factor out an e to the x out of both of these. So when I do that, I'm going to take an e to the x out, and that's going to leave me with e to the h minus 1 over h. Okay, so the next example, now I'm looking at the derivative as h approaches 0, so I can just pull this e to the x out front, and then I'm going to be left with the limit as h approaches 0 of, because there is no h in this part of the function, so this can just come out here. But I do need to evaluate this function, e to the h minus 1. Okay, we're at a bit of a standstill now because we don't know what this equals. Okay, so I need to know what this is. All right, so if I graph the function, so let me bring up a graph of this function. I'm going to graph e to the h minus 1. And here's a graph. This is the graph of e to the h minus 1. And we want to know what the limit is as h approaches 0. As h approaches 0, it's very obvious that this is 1. Okay, so when I go back to here, I know that this is equal to 1. So I'm going to say that this is just simply going to be equal to e to the x times 1, or just e to the x. So in conclusion, what we can say is that if you take the derivative of e to the x, you just get e to the x. So for the sake of chain rule, if you take the derivative of e to the u, then let me clear this up. I wanted the derivative of e to the x, okay? So now if I take the derivative of e to the u, it's going to be e to the u, but chain rule says I need to take the derivative of u with respect to x, okay? So let's look at an example that applies this. This example is like number 10. And number 10, it says y equals e to the x squared, and you want to find the derivative. Okay, so if I want to find the derivative, that's first derivative, I'm going to then say it's e to the x squared, but according to this, I need to take the derivative of x squared. So this answer would give me e to the x squared times 2x. So if I clean it up, I'm going to end up with 2x e to the x squared. Okay, so let's try another one. This is like example number 5 in the book. So say we have to do y equals e to the 2x over 3. Okay, so then the derivative is going to be e to the 2x over 3 times the derivative of 2/3 x. Okay, so that's going to give me the derivative of 2/3 x is 2/3, and this just stays the same, so it'd be e to the 2x over 3.